we're looking at in this video is the basics of our electrophilic addition reactions. These are centered around the alkene functional group. So we want to address some of the basics of the alkene before we continue on. We've already looked at our alkyl halides, and the alkyl halides, hopefully we could remember that they have an electrophilic carbon because they have that leaving group of a halide, or really any kind of functional group that would act as a leaving group. The alkanes we haven't addressed yet, but that will pop up in a video perhaps kind of randomly, if not at the end of the semester, and that's going to be for radicals. So, characteristics of the alkene. Some random naming issues that could potentially show up. You can hear them referred to as olefins. Terminal is in reference to an alkene at the end of a chain. And internal is an alkene in reference to inside the chain, anywhere inside the chain. Their intermolecular forces are London dispersion, but they do tend to be kind of stronger London dispersion forces because of the possibility of that pi bond interacting. What do we mean by that? If we go down and take a look at the bottom down here, if we look at the geometry around that carbon, it's trigonal planar, sp2 hybridized. Because it is sp2 hybridized, there is no need to show a wedge and a dash. We might end up showing that as a way to highlight the fact that we have empty p, or not empty, but we have p orbitals that are both above and below the plane of the molecule, and that if we take that structure and just kind of turn it so it's coming out of the board, what we can do is see those p orbitals overlapping to make that pi bond now in the plane of the paper. This is going to become important because that means our electrons can exist both above and below the plane of the molecule, which means when those electrons go out and react, they could end up with a new bond aimed up, or a new bond aimed down, which means the stereochemistry of your product could potentially be inverted, and we'll address that later. Degrees of unsaturation is kind of a pseudo maybe important thing if you wanted to look at degrees of unsaturation. The formula is there: C for carbon, N for nitrogen, X for halogens. In our formula, note that you won't see oxygen or other elements in there. Oxygen doesn't show up because it doesn't affect our unsaturation, and other elements just won't show up, so you don't have to worry about them, at least when calculating degrees of unsaturation. So yeah, that's where we're starting. So yeah, that's our degrees of unsaturation formula. After that, it is something that we're going to have to worry about, our cis-trans isomerism. So we've got the same kind of basic rules reviewed here for our nomenclature and deciding if we have cis and trans. Okay, so we'll real quickly draw out an alkene to reference this rule. So cut the bond perpendicular. Star your priorities. I'm going to go through and just say star and star. Okay, and then cut parallel to the pi bond and see how those stars are related. Okay, if they're on the same side, then they're cis. If they're on opposite sides of that parallel bond, then they're trans. I will say that opposite side has to be on different carbons. So for instance, if we went back, and I don't think I've ever said this, so I do apologize if that's screwed you up in a couple cases. If we did something like that, that won't count. Okay, why won't that count as well? That invalidated our cut the bond perpendicular. Okay, so we could, in theory, could never encounter that. But if you weren't following those steps, you may have tried to do something like that. So, nomenclature, yay, all of our rules, there they all are. You would need to go through and apply them. We will probably see, and by probably we will see, the alkenes and the alkynes show up in this unit. The alkenes is the primary driver here, but alkynes are going to do similar chemistry because they're just an extra pi bond. That's all that's really changing. So we've got a bunch of practice laid out here as one of the things to pick up speed within this lecture sequence. I'm not going to walk through the solve for these, but what I will do is give you an opportunity to pause, and then the answers will appear in a matter of seconds. So I'm going to ask that you go ahead and pause the video, space, click the picture, do something to make it stop. So there are all the names and all of my work associated with them. I want to call attention to some things as we go through some of these. Upper left with our pen to ine, don't lose carbons with that triple bond. It is incredibly common for students to lose or miss counting a carbon. When we move to the next one, that one becomes challenging because our largest carbon chain, the longest carbon chain, bar none, doesn't contain the highest priority groups. So you end up having to circle a smaller carbon chain because it has the highest priority functional groups within it. Okay, so be aware of that. It has to contain those highest priority functional groups. And then that one also becomes more difficult because we have the EZ nomenclature that we have to get thrown in front of that. Lower left, whoops, I just noticed I made the mistake that I was going to tell you not to watch out for. Make sure you include the cyclo in there. 3-methyl cyclohept-1 ene. That methyl group does not get counted as part of the main chain because it's not in the circle. We can't count out and then back in. We'd end up double counting carbons, so that doesn't work. And then your numbering is going to start from your highest priority, which will be your alkene. It'll start running in sequence, trying to go from the highest to, how it's shown, unfortunately. And then the last one is a relatively straightforward one, except that we do have E and Z, and this one becomes fun. This was a student-suggested question, and for this very reason. Should this be 2Z for E, or should it be 2E for Z? Excuse me. And it turns out that the orange one is correct. How do we know that? Because we would dig into our rules. 2.2.3, Z gets priority over E. Why? IUPAC said so. Hopefully I didn't surprise you there with deleting everything. I usually warn you, but you can always just backtrack a few seconds. Okay, so after that, we've got our big summaries. So if we think through what we did in substitution, we didn't get anything shown like this. So this is the first time we're really seeing this. This is a spider diagram. We're starting from a particular representative molecule, and then we explode outwards with all the potential reactions that can come from it. So within this chapter, you are responsible for all of these reactions and reagents. And note, one of the things that's important about the spider diagrams is that you try to pick something particularly useful in the middle so that when you explode outwards, you see stereochemistry, you see regiochemistry. So you know where those pieces are supposed to be falling. So these spider diagrams, if done well, and sometimes mine are and sometimes they aren't, have a lot of information embedded in them. Okay? And it very often gets ignored, but realize there's a lot of content built inside a spider diagram. What I would recommend, if you haven't done so already, is start working towards memorizing these. Why do we not see them in substitution? Well, in substitution, there are thousands, or probably thousands is a bit excessive, but for the sake of our class, tens of nucleophiles, and there's probably tens of leaving groups. Since those could go in any possible combinations, it would explode the spider diagram. It would just make it useless. Okay. So our alkene will determine the regiochemistry, where those individual pieces go, and some of that stereochemistry is going to be dictated by your reagents and their mechanisms. You may hear reference to this term Markovnikov and anti-Markovnikov. Just like with Zaitsev, which I don't think I ranted about, I don't like the use of these terms. Markovnikov in particular was able to make a structural observation that was pretty phenomenally precise without knowing anything about electrons. So Markovnikov came prior to Thomson with electrons, and he was able to make these cool observations. We now know something about electrons, so let's actually use the information we've got to explain what's going on instead of some very long dead Russian dude. Okay. The other reason why it becomes problematic is this term of anti-Markovnikov. A colleague who you may know, Laura, doesn't like that term as well for the same reason, that anti tends to push towards Newman projections, and that's not what the anti is referencing here at all. That anti is actually saying not Markovnikov. So it's the negative Markovnikov. So what you could go through and do is say not Markovnikov instead of anti-Markovnikov. I'm going to try my best to go to that or use that language because I think that's a good shift to try and pick up so it removes that confusion. Okay? So with that, we could go ahead and get started. Oh, but wait, there's more reactions that you also have to know. These are typically classified as our alkene oxidation reactions, because if we go through and look at these, and this spider diagram gets even more complex. Here's our center point, and we can explode kind of outwards from each of these pathways, but then some of those pathways have sub-branches that you need to be aware of as well. Okay, so that's why this one's organized in this fashion. These are all referenced as our oxidations because if we look at the end of each of those arrows, we end with a substance that has more oxygens than the previous one. So they're all oxidations, which is why they tend to get classified outside of the the electrophilic addition reactions. My argument is that they are still electrophilic addition reactions and should be grouped in the same category, but I am clearly in the minority on this, considering, from what I understand, no textbook classifies them that way. So, and still more reactions. Of course, if we do oxidation, we also have to do reduction. The reduction reactions at least are a little bit more simple. You're looking at the addition of hydrogen, okay, and Raney nickel almost always has hydrogen too. Okay, so we see hydrogen in all of its glory in cases, which can react with any pi bond. So we're looking at alkenes and alkynes. So if you see H2, add hydrogen. Okay. If you see H2 and words, then you can add hydrogen, but you only add it to alkynes. Okay, so it's a nice subtle change to this. If you see no H2, but you see sodium metal and ammonia, okay, you're still adding to alkynes, but the end result is a trans product versus a cis. Okay, so both of those reagents, the blue and the red at the bottom, are Lindlar's catalysts, and the sodium and ammonia are very commonly tested on because of their slightly different chemistries. They are selective for alkynes, and in the case of the sodium with ammonia, we end up with a different product. We end up with a trans product as opposed to the cis, whereas in all the other H2 reactions, all of those add cis. Okay, which in this case isn't obvious, so don't stress about that, but when we get to that reagent, we'll show that adds cis.